So the peak in these curves is given by Wien's law. If you look at the curve here corresponding to 5800 Kelvin, you'll see that temperature is more or less centered right on the visible region. Right, this is the region of radiation that our eyes can see, and this is the temperature that actually maximizes the amount of radiation, the fraction of radiation emitted in that temperature band. And I guess not surprisingly, this is the temperature of the surface of the sun, roughly, right? So, the surface of the sun is at a temperature that maximizes how much of the radiation that it emits is visible to us, right? And that's because our eyes have evolved to take advantage of that radiation. In fact, if you think about it, most of the things that you come into contact with every day are not visible to you, right? Most of the things we come into contact with aren't that hot, certainly not as hot as things up here. So we're dealing with things way down here that don't emit any visible radiation. So when we see them, we're relying on radiation being emitted by things that are up here, that are this hot, right? And that radiation bouncing off of those surfaces and hitting our eyes, right? So, it's kind of interesting how we perceive color based on what's reflected versus based on what's actually emitted. If I see somebody wearing a red shirt, that shirt looks red to me because red wasn't reflected from that shirt, right? Red was reflected from that shirt, and the shirt tended to absorb other colors, right? We had a project at one point in the solar energy lab related to full spectrum lighting that was kind of interesting, and it was basically this idea that if the colors that you want to see are not in the lighting, right, not in the spectrum given off by the light fixtures that are in the building, then you just won't see the colors, right? So if I'm trying to look at somebody that has a red shirt on, but there is no red wavelength bands in the lighting that's in the building, I won't see his shirt as being red. I'll see it as being black, right? And so full spectrum lighting becomes really important for retail institutions and things where you'd like to be able to go to a store and buy a shirt and then walk out and have the shirt look the same as it did on the floor of the store. So full spectrum lighting was kind of interesting, and one way to get full spectrum lighting, of course, is through skylights or other kinds of solar luminaires that get the actual solar spectrum into the store. And there's quite a bit of value to that if in the right stores. Okay, what else? I guess that's enough of this. You should sort of keep this in your mind in terms of how Planck's law behaves, right? There's a couple of this is getting weird. There's a couple of, I guess, terms that I'd like everybody to be familiar with and comfortable with. So spectral emissive power is one. So spectral emissive power, so this is E sub lambda. This is the emitted radiation per unit area per unit of wavelength, right? So this is the how the radiation is emitted over the spectrum, and is normalized by per unit area of the surface doing the emitting. It has units of watts per micron, right? So per wavelength per meter squared, so per area. And it is a function of wavelength. It's spectral. Whenever you see this word spectral, that means is a function of wavelength. So here's spectral emissive power as a function of wavelength, and maybe this curve right here is the spectral emissive power of whatever surface we're dealing with. Blackbody spectral emissive power, this is the emitted radiation per area per wavelength for a black body. This is what Planck's law gives us, right? So this gives us the upper limit on what that spectral emissive power can be. So whatever surface we have, this is some real surface in here, it can do whatever it wants, but it can never go above this EB sub lambda curve. The other term you should be aware of is this thing called emissive power, right? So this was spectral emissive power. This was as a function of wavelength. That's what spectral means. This is just emissive power. And this is basically spectral emissive power integrated over all wavelengths, right? So this is emitted radiation per area. And the way that I get that is I take the spectral emissive power and I integrate it over all the wavelengths. So this has units of watts per meter squared. This is the number of watts that a surface emits per unit area, right? And it may do that in some weird way where it's emitting more radiation at a low wavelength or high wavelength. That all gets lost in this integration, right? I'm integrating over all of the wavelengths to get the to get the emissive power. So it's the area underneath this curve. And then the blackbody emissive power is the same thing, right? It's E sub B. There's no lambda because it's not a function of wavelength. It's the emitted radiation per area by a blackbody. So in order to get the blackbody emissive power, I'm going to integrate the blackbody spectral emissive power over all the wavelengths. So E sub B is the integral of EB lambda from 0 to infinity, right? It's the area underneath this blackbody spectral emissive power curve. So the way to do that integral is you take Planck's law. So EB sub lambda is given by Planck's law, and you plug it into this integral, and you're integrating from 0 to infinity of this complicated equation as a with respect to lambda. And it turns out that highly not obviously, I guess, this integral ends up being sigma t to the fourth, right? So sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8th, and T is the absolute temperature. So sigma T to the fourth, watts per meter squared, and then Kelvin to the fourth over Kelvin to the fourth. This is watts per meter squared. So sigma T to the fourth is the blackbody emissive power, right? And the T to the fourth again emphasizes how the amount of radiation emitted is a very strong function of temperature. All right, this integral where you're going from lambda equals 0 to infinity ends up being this very simple formula, sigma t to the fourth. If you don't want to integrate all the way from 0 to infinity, so you're interested in how much radiation is emitted over some specified wavelength band from 0 to, let's say, lambda 1, then you'd have to do the same integral, but the limits would be different, right? So again, I'm integrating Planck's law, but instead of going from 0 to infinity, I'm going from 0 to some finite value of wavelength lambda 1, right? So in this case, I'm trying to get the area underneath just part of this curve. And it turns out that integral is not so simple. In fact, doesn't even have a closed form solution, right? So if you want to figure out how much radiation is emitted within certain wavelength bands for a black body, you have to use what are called external fractional functions, right? So external fractional functions it's basically a ratio. So the external fractional function gives you the ratio of how much radiation is emitted in the band you're interested in, so from 0 to lambda 1, divided by the total amount of radiation emitted by the same black body, right? So it's the ratio of this integral right here that we said had no closed form solution, right? So this is in watts per meter squared, divided by the total amount of radiation, which is just sigma t to the fourth. So that's what you have here. And it turns out that even though it looks like this ought to be a function of both temperature and this wavelength lambda 1, if you look at this, what you'll see is that, in fact, it's only a function of lambda 1 times temperature, right? So every place I have a lambda here, I also have a temperature. So here I'm going to multiply and divide by temperature. So I have d lambda t, and that gives me a t to the fifth on the bottom, which I can multiply by my lambda to the fifth. And of course, already I have a lambda t here. So the point is that I have one variable lambda times temperature, right? So I can integrate with respect to lambda times temperature from 0 to lambda 1 times temperature. And this fractional function then is only a function of lambda 1 times temperature. And that's why you'll see charts like this chart here, right? This is the external fractional function as a function of the product of the wavelength and the temperature, so micron Kelvin. And obviously if you go from a low value of wavelength, right, so now I'm moving this limit over to the left, the external fractional function is going to approach 0, and that's what it does. And then if I go to a high value of wavelength, so I move this over to the right, then I'm going to capture all of the area, and I'm going to approach 1, right? So 0 to 1 as I go from lambda times temperature close to 0 to lambda times temperature, closing in on some large number. These external fractional functions have been programmed for you in ease. There's a bunch of curve fits to them that make them pretty easy to use. In ease, what you use is the Blackbody function. So we're definitely going to need this, especially when we get to semi-gray surfaces. So we should look at how that works. So what the Blackbody function does is it takes in 3 arguments. The first is the temperature of the surface, and then the second and third are the wavelength bands. So if I type in F equals Blackbody, and then I want to know, let's say I want to know how much energy emitted by the sun is visible, right? So then the surface I'm talking about would be at 5800 Kelvin. The lower wavelength band is 0.38. Yeah, I can type 0.38 microns. And then the upper wavelength is 0.78 micron. Okay, so what this should give me then is the fraction of the energy emitted by a 5800 Kelvin black body that happens between 0.38 microns and 0.78 microns. This is a dimensionless number, F, right? And just to be clear, always the first argument is absolute temperature, and always these wavelengths are in microns. So if I hit solve, 46.6% of the energy emitted by the sun is visible to us, right? Which is, again, pretty cool. If I want to think about how much energy emitted by the sun is in the ultraviolet, so that would be now energy emitted below 0.38, right? So this would be from 0 micron up to 0.38 micron. This is the energy that's actually very dangerous to us, right? This is low wavelength, high frequency, high energy wavelength, and it turns out about 10% of what the sun emits is in that dangerous region. And fortunately, actually, only about 2% of this 10% makes it to the Earth. So 98% of this dangerous stuff is actually filtered out by the atmosphere, and that's what keeps us from getting skin cancer and keeps our crops from failing and stuff like that. And actually, the part of the atmosphere that protects us is the ozone layer. It's one of the reasons why having the ozone layer go away would be a really bad thing for life on Earth. All right, so that's an introduction to radiation, and in particular to black bodies. And so what we're going to talk about next time are how black bodies transmit radiation, how they transfer radiation heat between them. Black bodies being a pretty simple place to start in our kind of exploration of radiation, right? And we're also going to talk next time about view factors, which is our primary way of keeping track of where radiation goes once it's emitted.